So we're going to start here with Sn2 reactions. These are a concerted or simultaneous mechanism. So what we'll have is a molecule, and it'll have a halogen on it. There's our halogen. We'll have a nucleophile bristling with those extra electrons and a negative charge to boot. The nucleophile is going to attack this carbon right there. Why does it pick that carbon? Well, this is a halogen, remember? And it will tend to make a dipole by induction. This carbon is more positive than any of the other carbons. And so that's why that one is selected. The nucleophile attacks, let's draw, we got black. And if the nucleophile attacked and we didn't do anything else, we'd end up with 5 bonds on that carbon. That can't happen. So as this nucleophile attacks, these electrons are pushed off and go with the halogen. So here we had a 3-carbon thing, right? Yeah, 3 carbons. And the nucleophile is now attached in place of the halogen, and the halogen is like this. And it has these electrons have now been carried over, so they're with the halogen now. And the blue electrons from here are here making this bond. Okay, so this reaction is bimolecular. That's an Sn2. Now the rate is going to be equal to the rate constant, the alkyl halide concentration, times the nucleophile concentration. So if we look at these problems, see if I can pull it up, there we go. We can determine what will happen to the rate if the 1-ionopropane is tripled. We would expect the rate to be tripled. If the concentration of the ionopropane remains the same and the concentration of sodium hydroxide is doubled, the rate would double. If we double the concentration of the ionopropane and we triple the concentration of the sodium hydroxide, we get 6 times the rate. Now, what's very interesting about these reactions is that they are stereospecific. If we start with an R, we will end with an S. So if your carbon that's being attacked here is a chiral center, you will have an inversion of characteristics. And what happens here is that this nucleophile comes in. It cannot come in from this side. This bromine is large and this bromine is negative, and so it has to come in from the back side, and the bromine leaves from the front. This is our transition state. And the whole thing, the best analogy I can give is the whole thing flips like an umbrella. Is you attack this side, and then all of these groups get pushed to the other side. So if we want to draw these products, we will start with, and I have to tell you the way I usually draw these is I draw them and then see which one I've drawn and then determine how I want to proceed. If I have to change it, I can always change it. Okay, we've got a sodium here in solution. That sodium disappears. And it's really, this nucleophile is sitting here like this with a negative charge. Okay, and someplace up here that we don't really care about, there's a sodium with a positive charge. So these are just kind of stand-ins. So this is going to attack, get my other color, get this color here. Okay, this is going to attack right there, that carbon. And when it does, it'll flip the orientation. Okay, so this was a wedge. This was a dash. The sulfur will be on a wedge. It's just flipped. Okay, we could do the same thing with the iodohexane. Draw me a hexane here. And it's 3, so 1, 2, 3. And we've got iodine. It's going to be attacked by a chloride. That's our nucleophile. And the nucleophile is going to come right in like this and attack this carbon right here. Because it's just a little bit positive. We've got a dipole going on here. The iodine is pulling electrons away. And our product will 2, 3, and it will be on a wedge. Okay, so just whatever was on a wedge is on a dash, dash is on a wedge. And this one was S, and this one is R, this one is R, and this one is S. Okay. So the effect of substrate on the rate of the Sn2 process, we find that methyl groups react the most or the fastest. So this would be a carbon with 3 hydrogens and a halogen attached to it. Next we have primary. Well, let me do that. We'll just keep the X. Primary. Then we have secondary. And we find that tertiaries are basically unreactive. Tertiaries do not react. And the reason for this is we can see up here with this diagram, if these groups here are large and bulky, they obscure the sight. And so the nucleophile, I don't know why, the nucleophile can't get in there. Sorry about that. A little senior moment there. Okay, so let's look at transition states. This is a concerted process. So what we'll have, this is the carbon that's of interest. So that carbon right there is here. And we'll draw everything else in blue. This carbon is attached to hydrogen. It's also attached to another hydrogen. And then it's attached to this ring. We're doing a transition state, so we're going to have a bromine here. We'll do pink. Bromine. That bond is breaking, and we're going to have a hydroxy that we're making the bond. So this one is being made, or make, and this one is being broken. So it looks like this carbon is attached to 5 things, and in fact I have drawn 5 things, but it's really only attached to 4, because this one is being broken and that one's being made. They're kind of in between with things. Okay, so let's look at this one. This is the carbon. Oh, I really want to do a color. There we go. That's the carbon of interest. So we'll draw him here. That's our carbon. And it is attached to 2 hydrogens. We'll go back to our blue for the hydrogens. And it's attached to, looks like ethyl group. On one side, it's going to have an iodine. Those dots mean that it's being broken or being formed. It's not a full bond. It's not a real bond. And on this side, we have dots. We've got an oxygen, and that oxygen is attached to a carbon. It's attached to a carbonyl. So that would be the transition state. The dots are showing that those are not full bonds, they're being made and broken.